RubbleSpaceTelescope.
I'm Sajeev.
I'm Vanya.
I'm Sam.
I'm Kat.
And I'm Hassan.
So our mission for building Cubesat this year was given by the Woods Hole Oceanographic Institute, and we were to model a mission where our Cubesat takes pictures of the ocean's surface from orbit and identifies pieces of plastic on the ocean's surface. So the way we model this mission, you can see our mission set up on the upper right hand. We rotated our Cubesat in a 2-foot radius circle, and we captured multiple images per orbit that we then sent to our ground station, which in our case was our laptop or computer. And then once the image had reached ground station, we ran image processing code on it to finally output the percent of plastic, the percent of area that was covered by plastic, the percent of each color of plastic, which in our case was red, green, and blue, and finally the total number of plastic or the total number of pieces of each color on the board. Requires stuff like that to help us with our orbits. We were required to use Bluetooth to communicate with our Raspberry Pi, and we were required to use a Raspberry Pi camera.
All right, so this is the design process and how we implemented those requirements into an actual system. So the Cubesat is a complicated system made up of several different subsystems that work together and interface together to make the final product of the Cubesat. These subsystems include the payload subsystem, structure subsystem, comms, attitude, determination, and control system, and the power subsystem. So we split those subsystems up, and for each subsystem, we assigned one person to kind of make the code or build that part of the system. Throughout the process, we would talk to other subsystem heads and kind of learn how to interface them and build them by ourselves. And in the end, we integrated those subsystems together to create the final Cubesat system. So this is a ConOps, or a concept of operations, detailing kind of how the whole system is going to work together and what's going to happen on flight day. So to go over it kind of quickly, the first thing it'll do is boot up the Pi, which is kind of the brain of the operations. Pre-launch, it'll send a telemetry packet, which is a text file including information about the subsystems and if they're working, to the ground station, which is the laptop, over Bluetooth. After the ground confirms that they've received that telemetry packet, the Pi will check which orbit it's in, which if it's the first, it should be the first orbit. And it'll go into the capture orbit, which is the orbit where it takes the pictures of the posters when it detects that it's over them with the IMU. Once the IMU determines that the Cubesat is over a picture, it'll make the payload system, which is the camera subsystem, take a picture of the image and then process it. That image will be stored in a folder and will be downlinked to the ground station over Bluetooth, which is the comms subsystem. After that's done, the ground will confirm if they have received the image. If they do not confirm that they received the image within 30 seconds, the Pi will try to retransfer those images over Bluetooth. If it goes through another cycle of that and it doesn't transfer, the Pi will reboot and start everything over again. And then that transfer orbit is a separate orbit from the capture orbit. And throughout the 10 orbits that happen, going over the posters 10 times, there will be 3 capture orbits and around 7 transfer orbits, kind of switching on and off throughout the whole thing.
So this is just a function that we made in the main code, and it's basically part of the comm subsystem. And what it does is it goes through all the photos that we've taken and it tries to send them through Bluetooth to the ground station. And after it does that, it tries to read a signal from the ground station to ensure that it has a stable connection. So we give it 30 seconds or 10 tries to download this file from the ground station, and it tries to read from it. And if it doesn't detect anything, then it will basically we can have it reboot, or we can have it try and reconnect to ensure that we have a connection. And so these are some of the budgets that we've made. So these help us basically ensure that we have enough time to send the images that we get. So the first one on the top is the link budget. And it basically has a bunch of information that we've determined by measuring the downlink transfer rate is 34 kilobytes per second on average, and that will change throughout the orbit, but that's the average rate that we use for our calculations. And so with the image dimensions, we're able to calculate the size of each image and how long it will take to transmit one image. And that lets us know how many images we'll be able to send for orbit, which is an important number because it basically determines how many images we'll be able to get from our mission.
So the bottom is our power budget. So like Sam and Hassan talked about earlier, basically we were told that we can do 10 orbits and we have 10 minutes to do it. So we use the link budget and the power budget to determine what we're going to do, what state the Raspberry Pi will be in, and we decided to split it up into 5-second intervals. So basically, not looking at all the numbers and looking at the modes, you can see that there's multiple modes that we have, that different states that the Raspberry Pi can be in, whether it's taking images, processing images, or sending down images. And so we use the power draw in each of these to determine whether our battery will be able to supply enough power for the entire orbit cycle. And if we would need to generate any power using a solar panel, which we discovered that we didn't need to.
So throughout this process, we also needed to create a physical structure for a CubeSat that would house all the different components and also fit within the constraints of a 1U CubeSat. So we made this computer model that shows our Raspberry Pi, our inertial measurement unit, our battery, solar panel, a 10 centimeter by 10 centimeter by 10 centimeter cube, which is the size of a 1U CubeSat. Our CubeSat also needed to be less than 1.33 kilograms in weight, which we created a mass budget to determine. In total, our CubeSat turned out to be around 500 grams in weight, which was pretty much perfect. We had plenty of room to play with and to get everything right within our CubeSat.
All right, so now we're going to talk about what actually happened on flight day, which was on Wednesday when we tested our system. All right, so as Sam talked about earlier, what we did between each flight was send down telemetry. So the way the flight worked is the people on the ground station had no idea what the CubeSat was doing, just like a real CubeSat. So once it's launched into space, the people on the ground don't really know where the CubeSat is or what it's doing until it sends down data packets. So because we couldn't see the CubeSat physically, the people on the ground had to determine what's going on through these telemetry packets. So as you can see in the first line on the left image, it talks about how an image didn't include a poster image. And that's actually an error that was determined by the IMU. So one of the errors that we had is sometimes it would take images at the wrong spot, not over a poster board, because basically our inertial measurement unit had to determine when the CubeSat was over a poster, because we didn't know where the CubeSat would start. And sometimes it would have an error with its position just because of the accuracy of the sensor, and we would be not over an image. And not being over image also threw an error for the camera processing, which is another error that we used to get. So the data here on the square sizes and the color percents usually had lots of inaccuracies, and we can see some of them on the next slide with the flight images.
Some positives.
So we were pretty proud that
we
we
were
were
actually able to transfer lots of data,
send
to
up
our
telemetry, so we
CubeSat
just
and
wanted to
get
edit on all the good things that
lots
we
of
did, and we
images
thought we
along
were
the way.
successfully able to
And
get
transferring them was
images
actually a
and
struggle,
telemetry
and being
sent
able
up,
to
which was a pretty
manipulate
difficult task
sensor data
considering
to
the
make sure we're
Bluetooth
taking
modules
images
we
to
were
the right
working with.
places.
And we're pretty
It was pretty
proud that
difficult
over the
for us to figure
past 4
out,
weeks
but
we
we
were able
were
to
very
come so
proud that
far.
we were able to